Because we have been discussing diffraction and understand that at least a little bit at this point, I'd like to discuss briefly a practical application, which is telescopes, and in particular the lenses of a telescope. And what you want to do with a telescope is bring in the image of an object very clearly, magnify it, make it brighter, and increase the resolution or have a high resolution image. But there's only, physics, the laws of nature only allow so much of that benefit. It's not infinite. You can't observe a little mouse scurrying around on Europa, even if a little mouse is there, which it's not. But, point is, physics does not allow that to happen. And we have an ability to understand why at this point. So, basically, the resolution is the ability of the lens to produce distinct images of 2 points, real close together, like a high resolution. An example of that would be HD, an HD video versus the old, 140, 240, 360p type videos, which you can't see distinct objects very close together. But if you're talking about 1080p or 1440p, and even up, then, you can see very tiny, distinct regions on your screen and make out what the objects are. All right. Now, for lenses, you have something called aberrations, which are imperfections, and we'll get to that later. This is not a bad topic to talk about when we study optics a little bit more, but it's also good to put into here, which is why I am. So we don't know much about lenses, but that's okay. Actually, you don't need to know much about lenses. It's a little hole. All right, and that hole turns out to be a slit. But the thing that I want to focus on is not other aberrations of a lens, what it does to color and the focus and whatnot, but it's the diffraction that results from light passing through and opening the lens itself. Okay, that you can't fix because the wave nature of light, as we've been discussing, causes the diffraction to occur. You can't undo the diffraction, the bending of the light, because of its interference, as we've discussed. So again, what's a lens? Well, because it's not an infinite hole, so to speak, it's basically a slit. It's just a little round slit. So an image of a point object like a star, which is often what we want to look at out in space. Astronomers are interested in the stars, of course. And they really produce light like a wavefront coming into the lens of the telescope. And so that lens is a little slit. So, or it might be into your eyeball, your retina, through the pupil. Doesn't really matter. But it actually produces a little diffraction pattern. It will do that. And therefore, even if you take all other issues, aberrations away from the lens, you still get a blurry image. And that's a little bit loosely stated because blurry often denotes being out of focus, and this is a little bit different. But nevertheless, you can't get a perfectly clear image where you can clearly distinguish the features, the particular whisker pattern of that mouse, because he made a super duper telescope. It's impossible to do. So when light passes through a slit, the light interferes, produces a minimum on either side. When that slit follows the following relationship, sine of theta is lambda over d. Now, initially we called d A. All right, but I'm going to use d here. D is the slit width. And that's where that has to be satisfied to find where the minimums are. So the d is actually the diameter. That's the slit width. But because it's not a skinny slit, it's a round, it's not rectangular, you might say. It's circular. It turns out that that is equivalent to a slit of 0.82 times that diameter. And that's not that important, but just to give you the particulars. That particularly is what it is. And so when you factor that in, then when sine of theta is 1.22 lambda over d, that is the angle from the source where you get minima occurring. So that's the start of understanding how a telescope is diffraction limited. So what kind of image is produced by a telescope trying to magnify the image of a star and get a very clear, highly magnified image of it? Okay, what does that produce? Well, it looks something like this. So you see the diffraction pattern here. There's a large bright center and then the subsequent rings. And this is really indicative of the graph down here, showing the various intensity levels, like we've seen in our experience with diffraction so far. So because this is no longer just a beautiful image of the star magnified, you got these rings. This is a point source of light, essentially, what a star is. So what does this do in terms of limiting resolution? Well, if you have stars really close to each other, these diffraction patterns start merging onto each other. And at some point, they become a single image, and you just can't tell the difference. So here is the diffraction pattern. Say object number 1. We've got the maximum and the minimum. And let's look at object 1 as, say, a star. And the second star, here's a second star, at a different position in the sky, a different angle, so it produces its diffraction pattern in a slightly different place, say on the same detector, on the same screen. Well, if these are highly separated, then it's no problem. You can see the two stars distinctly. But as these get closer and closer, these are infinitely sharp regions of intensity variation. Okay, it's not like all the it's not like all the light from the star is just right at this one point. It spreads out because of diffraction. So the images are resolvable when the center of the diffraction of one disk, the center of this one, ends up being directly over the minimum of the other. That is called the Rayleigh criterion. And so that is how we define the resolvability of the stars. And it tells you what angle in the sky they can be separated from each other. And I'll show you that in a better picture in a minute, but it tells us also then what angle the sine of theta being equal to 1.22 lambda over d specifies. Is the equation where you arrive. This is the bright spot of object 1, where you arrive at the minimum. It's the same thing from here to here. It's basically, this is the condition. Well, this is what specifies that condition. Where do you get a minimum? You get it when this is satisfied, when the sine of the angle between the two objects is 1.22 lambda over d. So here's our lens, which is like the slit, and here's a diffraction pattern of an object, namely one of the stars. So here's a star producing this diffraction pattern through this slit, which is the telescope. And all right, so we can just draw a line from there through the center of the lens and show kind of the geometry of this thing. Well, the other star can be here. You draw through the center, where you get the bright region here, and the minimum occurs right underneath the maximum of the first one. That is the Rayleigh criterion. It is that transition where you can say, yeah, it looks like it's two stars rather than just one. It's right at that transition point. All right, so a telescope is said to be diffraction limited when it means that you can actually see that diffraction pattern, like this here. This is idealized, but really good telescopes, you'll actually see that diffraction pattern, which has to be where you have to push the power of the telescope, so to speak, to the point where the other aberrations would normally often be an issue. So you have to have everything just right. So the limits of physics are what's limiting the resolution rather than other imperfections of the lens and characteristics that you can't easily control, but maybe you can a little bit. Okay, so that's not a very clear explanation to require further discussion, but astronomers are really happy when their instrument, their telescopes, actually produce a diffraction pattern. It means they're pushing the limits of what the telescope can conceivably do. You can't overcome this, but you've been able to make a telescope good enough that it actually will show that diffraction pattern before it gets like so blurry from other limiting factors. So here is a graphic of what I mean, what this is all about. If you look at this first one, you see two separate stars. Yes, the diffraction pattern is shown there, but obviously you can see them as two separate objects. If you look at their individual diffraction patterns, they're separated quite a bit. And the peak of this one is way over here, way beyond the minimum of the first one, say. But in B, this peak is right above the minimum of the other one. This is that transition where it's resolvable as two objects, but you would probably agree with me where you might say, well, just barely. Yeah, here it's obvious, here it's not so obvious. This is the criterion for resolvability. And then in the last one here, it's, it looks like one object. There's really two objects, but they're separated by such a small angular separation. Really, the objects, if everything was perfect, they would look like points. These are, spatially extended in the image. And because of diffraction, they just merge onto each other in such a way that it just looks like one single object. So there, hopefully, is a little more clarity as to what this looks like. And finally, I'd like to just give an example of the Hubble Space Telescope, which is really an awesome instrument that was launched in the 90s. It's got a 2.4 meter objective lens. And actually, it's not a lens, it's a mirror. I apologize. And that's kind of important, but nevertheless, for our purposes, the whole idea of diffraction holds true with a mirror versus a lens. Now, the atmosphere typically limits the resolution of earthbound telescopes to about 60 arc seconds, to a half an arc second. And actually, it's the latest technology is even better than that. But for our purposes at the moment, without considering what we've been able to do to overcome some of these other obstacles, the atmosphere limits how much resolution you can get out of a telescope. So half an arc second, 60 arc seconds in a minute, 60 minutes to a degree, so it's a really, really tiny angle. And so that's going to tell us how good the telescope can do. And, it's, if we can get a smaller angle, half an arc second is pretty small, but even smaller, we'll be able to see separate stars even, with smaller angles between them. And that's the goal. You can see more stuff out there. All right. So earthbound telescopes, theta the angle is a half of an arc second, so it's a half of a 60th of a minute, a 60th of a degree. So you have to apply that twice, and you get a very small degree, a very, very small angle, 1.39 10 to the negative fourth degrees. But the Hubble Space Telescope is really an awesome piece of technology, and it is diffraction limited. And you can prove that by looking at the diffraction limited angle, which is given by this formula. Now the wavelength is about 550 nanometers. That's the middle of the visible spectrum, so we'll use that. And d, the diameter, is 2.4 meters. So you plug that in and you get 2.8 times 10 to the negative 7. So theta is the inverse sine of that, which gives us a tiny angle which is almost 10 times better than what you get with the limitation from other factors that are not, intrinsically non-overcomable, as is diffraction. So this is the best it could possibly do. And it is doing that. It's out in space, not affected by the atmosphere, so that's a really small angle. But therein is why you can't see the whiskers on the mouse on Europa, because this -5 would have to be a much smaller angle. Maybe, I don't know, I'm going to guess -15 or something. Some crazy amount of resolution that the laws of physics will not allow.